Okay, I'm Ross Gayler. I work for a company called Connected Analytics, which is a small consultancy. It's a data analytics consultancy, but because of the backgrounds of the people involved, it's primarily in the credit and risk area that we do our work. And within that, I'm one of the analytics specialists. So if there's anything that gets particularly tricky as far as analytical work goes, it tends to come to me. Or if there's anything where people want, hey, let's do something new, then that tends to come to me.
Right. So maybe you could give a little fuller background of the credit industry and how it got connected into data analytics.
Oh, long story, this one. This goes back to the Second World War. It was with mail order retailers in the United States. With the dispersed population that the US has, mail order has always been very big there, selling stuff out to the farm-based population, the rural population. And a lot of that was sold on credit. And so they had subjective manual evaluation of people's creditworthiness. And with the Second World War, they found that their credit assessors were being called up and were going off to war. And so it happened that one of the senior people at one of these mail order houses had a background in statistics. And he thought, let's have a go at doing this with some statistics. So he used what was essentially discriminant analysis to build a very simple model which took the information from their standard application form and converted that into a score, such that the score was related to the likelihood that the person would repay that what's effectively a loan, the purchase on credit.
That's pretty interesting. What was it, Sears Roebuck by any chance?
I can't remember. I'd have to go
World
on.
War?
It could well have been Sears Roebuck. I would have to go back and check on that. But that then was a relatively low frequency of usage of that sort of technique from then on. The difficulty was the absence of computational horsepower. So scorecards, and so the technology was called a scorecard. So literally it was a sheet of paper and it had various items on it like how long have you been living at your current address, how old are you, do you own your house, are you paying a mortgage, and so on. And attached to each of those would be a number of points. So if you'd been at your current address for less than a year, then that might be 0 points. If you'd been there from a year to 2 years, that might be 5 points, and so on. And literally the person who was assessing the application for credit would then just go through, tick all the relevant boxes, add up all the points, that's your score, and that score is then gives you an estimate of the likelihood that you'll default on that credit arrangement. And it continued on in that way, very low uptake, until perhaps I think the 60s. And then there was a company in the United States called Fair Isaac, which were some ex-operations research guys, who the computer power finally started to become sufficient to allow it to be easy to go away and develop models on relatively large samples of data, where relatively large might be a couple of thousand observations. Their real innovation actually was in the data preparation side, because in those days, if people were going to a bank to get a loan, you'd be going to the local bank branch, everything would be on paper, so all the information they needed was stored on hundreds of sheets of paper, stored in the filing cabinet in each different bank branch. And so their innovation, which allowed them to actually make a business out of this, was the way they mobilized people to do the data entry work so that they could get this data entered in a standardized form at a reasonable cost and in a way that was fit to be used in a statistical model development.
So that means card punch to mag tape or something.
Yeah. In those days it would have been probably even manual card punches.
Right. So I guess the data analytic part of all of this is where the weights come from. When you're doing these questionnaires or whatever,
Yeah, correct.
the weights are determined by, as you said, discriminant analysis. Maybe you can describe that just very briefly for our audience.
Okay, discriminant analysis, if you haven't come across it, is effectively you can think of it as the same as a multiple regression problem, but where the variable, the outcome variable that you're trying to predict, only has two values, indicating, this is in the simplest form, the membership of one of two groups. So traditionally in credit scoring, which is what this field of work is generally called, you assign to each case, each loan, an outcome which is traditionally called good or bad. And this is not implying that the people involved are good or bad, it's just this is the outcome I would have preferred to occur, they paid me back, versus that's the outcome I'd really rather didn't occur, which is they didn't pay me back. So you'd assign these two groups, good and bad, and what you're trying to do is to predict that. Essentially, it does look exactly like a multiple regression. And you can do the same thing with a multiple regression, just with a 0, 1, or any two different levels of the outcome variable.
Right, it's classification rather than traditional regression.
Yeah, and that's an interesting question in credit scoring. So many people do treat it as a classification problem, but the way it's actually used in practice is as a regression problem, because what we definitely want from these models is something like a score which is finely continuously graded. We don't want to get back a predicted classification. We don't want the model to come back and say, you are predicted to be good, you are predicted to be bad.
Well, I would have said otherwise. I would have said that what you really want is the probability of default.
Ah, that's true. What you want is the probability of default.
Yes.
So you want the probability.
Many classifier systems are indeed probabilistic classifier
Yeah.
systems, not just these. Take the highest mode. Yes,
Yeah.
no.
That's exactly the point. What you want to do is to make sure that you get back a continuous, or an approximately continuous prediction, because this then gives the business control over that process. So if they want to say, I want to increase my acceptance rate by 1%, if you've got a continuous predictor, then you can change the threshold that you're comparing your prediction to by a tiny amount, and you get that tiny change in the acceptance rate.
Well, you could also plug that into a decision analytic model and figure out how much you're going to win or lose by making that change.
Yes, that's precisely the sort of thing you have to do in credit scoring. So in credit scoring, if you were to compare it to other branches of data science or statistics, the techniques that are used tend to be very, very straightforward, but there's a lot more emphasis that goes on to understanding your data, understanding the business, understanding the systems that these are going to plug into, because most of the problems which can arise are problems which are outside the statistical domain, they're in the practical domain around it. So the catchphrase, what could possibly go wrong, is probably the first thing that passes the lips of a credit scoring person, because their job is to consider everything that could possibly go wrong, which isn't reflected in the data you currently have in front of you. So you're building a model not just to capture the patterns that are in that data, but try to anticipate all the ways in which the data might be different in the future that you currently don't have access to, and try to make your model robust to those possible future changes.
Well, in particular, all the ways the model might be used or misused by the business.
Oh, absolutely. Don't get me started on businesses misusing models. But yeah, it's, because so much of in these kinds of models, we're not picking up on causal patterns, so they really are just associations. So things like, as I said before, how long have you lived in your current address? So obviously, how long you've lived in your current address is not causally related directly to the outcome of whether you're bad. It's, they're probably symptoms of some other things going on, and the reason that any particular individual happens to default on their loan most directly relates back to things that you're never going to get your hands on in a data set. Are they going to get pneumonia in the next couple of months? Are they going to get in a messy divorce and lose all their assets? Is the economy of the particular area where they live going to go down the gurgler, and so on? So these are things which can have a major effect, and you're never going to have access to them in the data that you have to hand for building these sorts of models. So the model doesn't have to be particularly good in an absolute sense. It just needs to be better than you could do by hand, so better than you could do in subjective decision making, and then have all the attributes you'd expect of an automated system. It needs to be repeatable, it needs to be fast, it needs to be cheap, it needs to be robust, it needs to be controllable, and you need to be able to give reasonable predictions of what you think would happen if you were to change some of the operating conditions.
So one way of summing up some of what you said is that you're really after prediction, probabilistic prediction.
Correct.
You're not after explanation or hypothetical interventions and how government policy might change the operating environment, for example.
Or to a much lesser extent than other fields, that's true. But you still have to worry about those things to some extent. So for example, in the United States, there is legislation which requires that if somebody is turned down for an application for credit on the basis of a credit score, which typically comes from a credit bureau in the United States, that the lender is obliged to provide an explanation of both, first to say, we declined you because of your bureau score, and then to provide some explanation as to how things might have been different. Your score was low because we can see that you failed to pay back the last 3 loans you took out, or you seem to have an awful lot of credit activity going on, and that's usually associated with people who are desperate for credit to pay off other debts and so on. So to some extent you need to be able to, with the models, explain why somebody got the score they did. It's certainly not the standard of causal explanation that you'd want in a scientific explanation.
Well, it's actually not the same causal problem.
No.
You're trying to explain why the credit agency turned down an applicant as opposed to why an applicant defaulted.
Yeah, and this, well, in this case, yes, it's not even why they defaulted, it's why we think that you're too risky for us to accept.
Yeah.
But also then that does get into other, because credit is a highly regulated area of commerce, we have to worry about things like privacy legislation, discrimination legislation, and so on. And then you have the regulators who are worried about the stability of the financial industry as a whole, and they're going to insist that if you have some lender who's using some model, the lender can actually explain what the model is doing, which means that things like neural nets, where you say, well, a lot of numbers go in one side and another number comes out the other side, and what happens in between, there's sort of
magic.
Lots of magic goes on in the middle, is not going to cut it with a regulator.
Right.
So
to whom do you have to explain these models actually?
we have to explain them to the lender, because the regulator won't touch us. They say, we're not the as an external vendor, we have no direct relationship with the regulator. It's up to the lender, who is our client, to be able to explain to the satisfaction of the regulator that they understand what they're actually doing and what they're controlling. So we have to explain it to the lender, who then hopefully has understood it well enough to explain it to the regulator.
And the lenders are typically banks.
Yeah, banks, credit unions. These days you have the various sorts of startups and so on who are getting into lending, peer-to-peer lending and so on.
Okay. And so you would say in Australia the representation in this modelling business of neural networks is what, 0?
I think it would be 0, yeah. I'm certainly not aware of anybody who's using a neural net in the credit risk decision. So this is the how likely are you to default decision. Reputedly they are used in things like fraud detection, although I have heard from the people behind one of the more successful systems in the United States, that although the system is described as using neural nets, internally effectively it's just a regression anyway.
Well, one could say that about neural nets in general.
Yeah.
Certainly if they're learned by background.
Yeah. So we do use, I'm aware of various lenders who are using more exotic techniques during development, but then effectively approximating that model using a standard regression for the final deployment. So you might, for example, use something like a random forest during development as a cheap and cheerful way of saying, well, a random forest is likely to pick up most of the variance that can be picked up from model from this kind of data. So we build a random forest and we find that the performance level is up here. We go away, build our regression model, first cut, and we find performance is here. Well, that's a significant difference. Let's put some more effort in. And we might use information we find out from the random forest to suggest various useful interactions. And then you basically chip away at the regression model until eventually it gets as good as the random forest.
Sure. Well, traditionally in science, it's a lot easier to solve a problem when you know there is a solution.
Yeah.
And basically, that's what you're talking about.
Yeah.
You go in and do some early model that is hard to explain, hard to utilize in dealing with management and regulators, and then you go and find something that's better for explanation, like a Bayesian net or a regression or what have you.
Yeah, and it is important to be able to explain. And the other thing is, it also is important to be able to explain not just from the regulatory reasons, but also for model robustness reasons. So the general belief in the industry is that if you find an interaction uh, unless you have a decent reason for believing that that's a stable interaction which is present for good systematic reasons in the environment. If it's just an unexplained interaction which you observe in your data, then it's probably ephemeral and it's not going to be there when the model is actually put into practice. So it's very important when you're developing these models is you do it interactively with the lender, with the client. And so you're showing them all the effects that you're discovering along the way. And if they can't come up with a good explanation for that effect, you typically leave it out of the model. If they're not comfortable that that's something that they believe will be there in a couple of years' time,
Right.
then it doesn't find its way into the model.
So you take model building to be a kind of iterative prototyping process where you involve your client from the beginning?
Yes, we do. I mean, it's not as iterative as it could be, as iterative as I'd like it, but that's sort of more the reality of being a vendor working for a client, and also the realities of the kinds of clients you're typically working with can't sustain that level of interaction. But certainly the way you'd structure a project is the client is very much involved in the setup of the project, and then there are 2 or 3 points along the way where you come back with interim results, walk them through it, explain what's going on, get them to explain what they think is going on, go back, rinse and repeat.
That's fantastic, because that's what I as an academic have been saying for years, but I
Oh,
can
it's,
use evidence from outside.
yeah, it's well. I mean, typically, if ever you find there's a really strong effect, your initial presumption is it's rubbish. That's strong effect almost always means that there's just some problem with the data. So I mean, as usual, you spend at least 80% of your time mucking around with the data, and the quality of the data is, despite it coming from operational systems, is usually appallingly bad.
Yeah.
And the bad in the sense that because it's been gathered over an extended period of time, and there have been system changes and operational changes during that, there are all sorts of unexplained discontinuities in the data.
Indeed.
Typically you can rely on the dollar figures being right. Banks tend to care about accounts balancing, but more or less anything else is just regarded as transient information, which is only used while we're servicing a customer, and then after that, who cares? And nobody bothers to consult with the data scientists when they're designing these sorts of systems.
Well, you can get some remarkable shifts in how data are recorded.
Yeah.
It can cause lots of problems. For example, the Bureau of Meteorology has been correcting temperature data because of changes in urbanization, and they catch an awful lot of flack from that from the naysayers. So.
And at least you can see it. There's a decent reason behind that happening. Whereas in these kinds of systems, because you imagine some of this data is generated from call centres and the like. And the data systems behind those tend to be a tad hokey, and you'll have some field which has some code in it which generally means something fairly cosmic, like this account has been frozen because of suspected fraud and what have you. So there'll be some set of codes which they'll use, and you'll go away and you'll find the complete set of codes that are used over the data set you have, and there are some things which turn up a few dozen times. And you go and ask the relevant people, no idea. Somehow or other these codes have just crept in, and it'll probably be, there was some period of 3 weeks where we really needed to capture some piece of information. So we just decided that we could fit it into this field, and we'll just use some code which isn't used for any other purpose and fit it in that field. And it's suited some purpose for a few weeks, and then...
And then they forgot about it.
Yeah.
Well, that's an interesting source of noise.
Yeah, so and that's been my experience for many years now, that if you sit down with a data dictionary and then back it up with a set of frequencies of all the values that are in there, even the people who really should know what's in their database, there'll be some fraction of the data which, who knows?
So how do you clean the data up? You said you sit with your clients and work through what their thoughts about it. Sure, but what else?
Well, what we have to do in those circumstances is try to code it in such a way that it's going to do least damage to the models. I mean, if it's something which occurs very rarely, then in a sense it really doesn't matter what you do with it, because on these kinds of models. I mean, it certainly is not going to affect the kinds of statistics you see at a portfolio level.
Right.
On
And
that.
those are more or less by definition outliers. So you
Yeah.
can probably just ignore them and model the mainstream.
It depends. Because what we have to allow for is that previously unencountered values can turn up in the future. The one thing, because this is always going to be in an automated system, the one thing we don't want is the system to be cheerfully going through calculating these scores and then coming to some particular case where we've got some input values we've never seen before and they're suddenly dying in a screaming heap. We have to be able to provide some kind of an answer on every occasion. So if we think that there's a possibility that these kinds of values might turn up in future but they'll be rare, we might map them to a value which effectively has zero impact on the score. So effectively that particular predictor might be ignored with respect to the calculation of the score. Whereas if we thought that there were some values which should never ever occur, and if they did occur, then something horrible has gone wrong somewhere else in the system, then in those cases we would not calculate the score. We'd set a special value to indicate we can't calculate a score because we think something horrible has gone wrong.
Sure. In computer science, the analogy is you have a system halt.
Yeah.
So you can figure out what's wrong.
Yeah. In this case, though, we're not going to halt the system. It's just
You halt the model.
we halt the model, correct, and you have appropriate monitoring going all the time. That if this occurs more than so many times in a session, then the whole system should grind to a halt. But if there's only a few of them, it just means, oh well, you just rely on the score from the previous month or something like that. But yeah, it's because all these systems are basically under the control of the lender. They can change at the drop of a hat, and the people who do the modelling are always the last people to find out about it. Usually the only way you find out about it is the score distribution seems to have shifted this month. I wonder what's changed. And then you work your way through all the systems, and eventually you go back and you can find some person somewhere else in the organisation. Oh yeah, we changed that last month because X, Y, and Z. Thanks for telling us.
Right.
But that's just the standard way these things work.
Yeah, you were saying neural nets aren't widely used or aren't used at all.
Yeah.
What kinds of models are? You had discriminant analysis leading to scores in the past. But
Discriminant,
what's happening
so
now?
I mean, as I was saying, it really is very, very straightforward modelling in mainstream credit scoring. So, and it was essentially driven by the availability of computing power. So I started credit scoring 20-something years ago, and at that point it was primarily linear regression was the method, not because it was appropriate, but because it could be done on a small PC. And at that stage, for the kinds of modelling we were doing, which was perhaps 10,000 observations and perhaps a couple of hundred variables, that might take 20 minutes on a PC of the day. And then we switched over to logistic regression, which is more appropriate, but in fact, practically there's no difference in the models. That's where the vast majority of credit scoring models still are. They're effectively logistic regressions. Now, as I was saying, people may have gone off and used random forests to explore the data. They may have gone off and used generalized additive models to try to convert from continuous variables to see how they should be rescaled or non-linearly transformed. But for implementation reasons, they tend to be converted to what looks like a fairly standard regression model. And in fact, the standard form for scorecards is actually to take continuous variables and just break them up into categories, into discrete categories, although that's less so over the last 5 to 10 years. The models have turned up that quite cheerfully take continuous predictors as well. The great breakthrough of the decade, continuous predictors.
Compute power continues to make those things more and more available.
Yeah, it's also partly constrained by the kinds of implementation engines that people have. So because if you're talking about application scoring, so this is somebody who's applying for credit. Typically this is done in real time, and that then means that the system which is calculating the model generally or historically has needed to be embedded in the lender's processing systems, which means it's been specialised software done by specialised vendors who have been quite happy to use techniques from 20, 30 years ago and don't see any particular need to change.
Looking.
Yeah, yeah. Whereas these days, I think there is a tendency more to, because more data tends to be coming from off-site. And when your data source is off-site, you've got no idea what sort of techniques it's using. People may well be using some scoring algorithms off-site as well, and if they're happy enough to do that, then they could be using more advanced techniques. But as I was saying, if they need to explain it to a regulator, or they need to feel comfortable internally that if I tweak this way, then that will happen as a consequence, then it still doesn't mean that they need to have perhaps more limited models.